Tesla's so-called Giga Press 4.0 is being described as the factory breakthrough that could arrive by 2027. But Tesla has not publicly announced any machine by that name, and the biggest press it has confirmed is the Cybertruck's 9,000-ton unit. The real story is still powerful. Giant castings can replace many welded pieces, cut factory steps, and pressure Toyota and Volvo to follow. Yet bigger castings bring higher tool costs and repair risks. So what upgrade is real, and what is internet speculation? The same problem surrounds the huge numbers attached to it. Some online claims describe a 50,000-ton machine capable of casting most of a vehicle at once. Yet IDRA Group, the Italian company that helped build Tesla's giant casting equipment, publicly lists presses reaching 8,000 and 9,000 tons. This catalog does not show an official Giga Press 4.0 or a Tesla-bound 50,000-ton model. What Tesla has confirmed is still impressive. Its 2024 financial update explains that a custom aluminum alloy and a 9,000-ton press are used to create large front and rear structures for the Cybertruck. Instead of joining many smaller metal parts through welding and fasteners, Tesla can form a much larger section in one casting. This reduces the number of parts and makes production less complex. Aluminum scrap from the process can also be melted and used again. The more important upgrade may not be its size, because Tesla is also changing how the whole car comes together. That means the 4.0 label should be treated as an unofficial name for several possible improvements. These could include stronger alloys, faster molds, better cooling, automated quality checks, larger castings, and Tesla's unboxed assembly process. Together, these changes could matter more than one record-breaking machine. So the headline is not confirmed, but the engineering race behind it is real. Tesla has already shown why giant castings can simplify vehicle production, and Toyota and Volvo are now developing their own answers. To see where a fourth generation might lead, the investigation must first enter the press Tesla already operates. A normal car body begins as a collection of separate metal sheets. Large stamping machines shape these sheets, and robots move them into position. Hundreds of welds, bolts, and fasteners then join everything together. Each step needs equipment, workers, floor space, inspections, and time. Tesla's gigacasting technology attempts to remove many of those steps. Gigacasting is a form of high-pressure die casting. Molten aluminum is pushed into a large steel mold, where it cools and becomes a solid vehicle structure. Instead of welding many smaller pieces together, the machine can create a large front or rear section in one operation. The process works a little like a giant waffle iron, but with far more heat, speed, and pressure. The mold has two heavy sides that close around an empty space shaped like the required car part. Hot aluminum flows into that space. Once the metal becomes solid, the mold opens and robots remove the casting for trimming and inspection. The 9,000-ton figure describes clamping force. It does not mean the machine drops 9,000 tons onto the aluminum or uses that much metal. The force keeps the mold tightly closed while molten aluminum is injected inside. Without enough force, the mold could separate slightly, allowing metal to escape or creating a weak and inaccurate part. For Tesla, the attraction is simple. One large casting can replace many stamp components, welding robots, storage areas, and transport steps. Fewer joints may also make the body more consistent. In theory, simpler production can reduce the cost of building each vehicle. That could eventually support lower prices, although Tesla has not said how much of the saving reaches each buyer. Tesla also says leftover aluminum from Cybertruck castings can be recycled. But a bigger press does not automatically produce a better vehicle. The alloy must flow evenly, the mold must cool correctly, and inspections must find cracks, air pockets, or other hidden flaws. Subscribe for more clear investigations into the factory technology shaping the next generation of cars. That difference between raw size and useful control is where the 4.0 story begins to split from reality. Useful control becomes harder as the casting grows. A larger metal part has more surface area, so molten aluminum creates more pressure inside the mold. That pressure tries to push the two sides apart. If the clamping force is too weak, the casting may lose its shape or develop serious defects. This is why Tesla uses a 9,000-ton Giga press for large Cybertruck structures. The number is confirmed by Tesla, and IDRA Group publicly offers machines in this range. It is already an enormous system. The press needs heavy foundations, large furnaces, robotic equipment, cooling systems, and precise controls. It is not simply one machine placed in an empty factory corner. The 16,000-ton figure has a different history. In September 2023, Reuters reported that Tesla was studying a way to cast nearly the entire underbody of a smaller vehicle as one piece. Sources familiar with the work said this idea might need a new press with 16,000 tons of clamping force or more. But Tesla had not chosen the machine or completed the vehicle design. That difference matters. Engineers studying a possible system is not the same as Tesla ordering it, installing it, or preparing it for production. The reported 16,000-ton press remained part of an unfinished plan. The rumored 50,000-ton Giga press goes much further. No reliable Tesla announcement, IDRA catalog, factory filing, or official technical document confirms such a machine for 2027. The figure may sound perfect for a viral headline, but there is no solid evidence connecting it to Tesla. Even if a press that large could be built, greater force would not guarantee greater savings. A bigger press needs stronger foundations, larger molds, more factory space, and greater upfront investment. If the casting develops a defect, more material may be lost. If Tesla changes the vehicle design, replacing or modifying the giant mold could be costly. Production volume matters too. An expensive machine makes financial sense only if it creates enough good castings for enough vehicles over many years. Speed without quality would simply produce defective parts faster. Tesla may not need the largest press ever imagined if it can change how every section of the car reaches final assembly. That new assembly method is called the unbox process, and it may be more important than any rumored press. In a traditional car factory, the vehicle body moves along one main production line. Workers and robots add parts in a fixed order. Each new step depends on the one before it. If one station slows down or stops, the delay can spread through the entire line. Tesla's unboxed method attempts to break that long chain into separate work areas. Major sections of the vehicle can be built at the same time. The front structure, rear structure, battery carrying center, cabin, and painted outer panels can each move through their own process. These sections are brought together closer to final assembly. It is like building several rooms of a house at the same time and then connecting them, instead of finishing the whole house one room at a time. This could let more people and machines work on the vehicle without standing inside a narrow, unfinished body. It may also reduce wasted movement and make better use of factory space. Giga castings still have an important role. Large front and rear aluminum sections can become two of the main building blocks. But this creates a major contradiction in the Giga Press 4.0 story. Tesla once explored casting nearly the entire underbody as one piece. Reuters reported in May 2024 that the company had stepped back from that difficult plan. Instead, Tesla reportedly chose a more proven three-part structure. This uses a front casting, a rear casting, and a center section that holds the battery. Tesla later said its purpose-built Cybercab would continue to use an unboxed manufacturing strategy. This suggests that Tesla does not need to create the entire floor with one giant shot of aluminum. It can focus on producing several large modules quickly and joining them through a smarter assembly system. That approach may reduce risk while keeping many of gigacasting's benefits. However, the promise still needs proof at full production speed. Separate sections must arrive at the correct time, fit together with great accuracy, and pass safety checks. One delay could still affect the final assembly point. A modular factory may avoid one giant engineering gamble, but it cannot remove the hidden costs inside every casting. Those hidden costs begin the moment a casting leaves the mold. From the outside, the part may look complete. Inside, however, poor metal flow can create air pockets, cracks, or weak areas that are difficult to see. Every large casting must be checked carefully before it becomes part of a vehicle. A defect in a small stamped piece may waste only that one part. A defect inside a giant casting can waste a much larger amount of aluminum and factory time. The metal can often be melted and reused, but the failed casting still consumes energy, labor, and production capacity. The molds create another challenge. Each one is a huge and highly accurate tool shaped for a specific vehicle section. It can be expensive to design, build, test, and change. If Tesla updates a small area of the vehicle, engineers may need to modify a major mold. Traditional construction can offer more freedom because one smaller stamped part may be changed without rebuilding the whole structure. Reuters reported that this high upfront investment was one reason Tesla stepped back from its one-piece underbody plan. The company could gain long-term savings, but only after spending heavily and solving difficult production problems. Toyota is attacking this weakness from another direction. The company says replacing a normal Giga casting mold can take about 24 hours. Using its own equipment and factory knowledge, Toyota developed a prototype method that aims to cut this change to around 20 minutes. If it works reliably at scale, Toyota could switch designs faster and lose less production time. Repairs also need a fair explanation. A vehicle with large castings is not automatically impossible to repair after a crash. The result depends on where the damage occurs and how serious it is. However, if a major structural casting is badly damaged, replacing or repairing it may be more complex than changing a small separate part. Repair rules, labor costs, and insurance decisions can then affect the owner. Would you choose one huge casting for maximum simplicity, or 3 sections for more flexibility? Explain your choice below. Tesla created the pressure for this change, but its rivals are now trying to remove the weaknesses Tesla exposed. Tesla's biggest manufacturing success may also weaken its future advantage. By proving that very large structural castings can work in production vehicles, Tesla gave other automakers a method they could study, improve, and adapt. Toyota is taking that opportunity seriously. The company has shown prototype gigacasting equipment at its Myochi plant in Japan. Like Tesla, Toyota wants to replace dozens of separate sheet metal parts with large aluminum sections. But it is adding ideas from the Toyota production system, which focuses on reducing waste, avoiding downtime, and fixing problems quickly. Toyota plans to divide its next-generation electric vehicles into front, center, and rear modules. Different teams can work on these sections in open areas before final assembly. Vehicles under construction may even move between work areas under their own power, reducing the need for fixed conveyor lines. According to Toyota, this combination could help cut production processes and factory investment roughly in half. That is a company target, not a result already proven across full-scale production. Still, the plan shows that Toyota is not merely copying the size of Tesla's machines. It is trying to make the whole system more flexible. Volvo is taking another route. IDRA Group announced that Volvo Cars ordered 2 9,000-ton Giga press machines for its planned electric vehicle factory near Košice, Slovakia. These machines place Volvo in the same force category as Tesla's confirmed Cybertruck press. Because the plant is being designed for electric vehicles, Volvo can shape parts of the factory around large castings from the beginning. Then there is BYD. Its wider threat does not depend on owning the biggest casting press. BYD competes through manufacturing scale, battery production, a broad vehicle range, and strong pricing, especially in China. Tesla must therefore save money across the entire car, not just its aluminum structure. Tesla still holds valuable experience from using gigacastings in real vehicles. But the basic idea is no longer exclusive. Toyota may challenge it through flexibility, Volvo through new factory equipment, and BYD through cost and scale. By 2027, the winner may be decided by factory results that cannot be measured in tons. Factory results bring the investigation back to the name that started it. Tesla has not officially announced a product called the Giga Press 4.0. It has not confirmed a 2027 launch, a 16,000-ton order, or the rumored 50,000-ton machine. Those claims should not be presented as completed technology. The confirmed foundation is smaller, but still important. Tesla uses a custom aluminum alloy and a 9,000-ton press to create major Cybertruck structures. It has also continued developing the unboxed manufacturing idea, where large sections can be built in parallel and joined near final assembly. For the title's prediction to become true, Tesla must provide much more than a machine name. It would need to reveal the new casting system, identify the vehicle and factory using it, and show stable production at real scale. The company would also need to prove that the process reduces parts, time, labor, and factory space without creating unacceptable defects or repair costs. Tesla's strongest advantage is its ability to design the vehicle and factory together. Instead of building a car first and then deciding how to produce it, engineers can shape the castings, battery structure, assembly process, and production equipment as one connected system. Its largest weakness is flexibility. The bigger and more integrated a casting becomes, the more expensive it may be to change. Large molds require major investment, and one defect can affect an entire structural section. A sudden design change or drop in demand could make that investment harder to recover. So Tesla could deliver its biggest manufacturing upgrade by 2027, but it may not look like one mythical press. The real breakthrough could be a coordinated system of proven castings, modular assembly, better alloys, faster inspections, and smarter factory software. If this helped separate the confirmed technology from the online claims, like it and share it with another EV fan. If Tesla can turn those ideas into reliable savings, customers may gain more affordable electric vehicles, while rivals will face pressure to rebuild their own factories. The future factory will not be won by the boldest machine name, but by the lowest cost that survives